If you look up at the sun right now, well, don't look directly at it, obviously, but if you look up at the sky, classical physics basically dictates that our star should be pitch black.
Right, completely dark.
Yeah. The core of our star is sitting at around, what, 15 million degrees Celsius?
Just about, yeah.
Which sounds incredibly hot to us.
Oh,
But mathematically speaking, it is actually thousands of degrees too cold to force protons together.
it really is.
So the sun is technically too cold to shine, yet obviously, it does. And the only reason it does is because of this microscopic loophole in the very fabric of reality.
A loophole that literally keeps us all alive.
Exactly. Welcome to our deep dive. I want you to just sit back, let your shoulders drop, and let the noise of the macroscopic world sort of fade away for a while. We are taking a really relaxing, unhurried journey into the quantum realm today.
It's gonna be a fun one.
And before we begin, please remember to like and subscribe to this video brought to you by Decoding the Dark. Our mission today is to completely explore quantum tunneling.
Which is arguably one of the most mesmerizing, counterintuitive phenomena in all of physics. I mean, we are looking at a process where particles just move right through solid, impenetrable energy barriers.
Like magic, almost.
Yeah, exactly like magic, but it's math. And we aren't just going to look at the theory, right? We are diving deep into the actual mechanisms of how this powers modern flash memory, how it threatens the future of microchips, and how tomorrow's quantum computers are fundamentally built on this exact reality.
And we've got some great sources for you today. We're drawing from foundational physics texts, some really fascinating university lectures, and even some incredibly recent patent landscape reports.
Fresh off the press, basically.
Right. And we are going to navigate all of this at a very gentle pace. You don't need a degree in physics to follow along. We'll lean into the weirdness, but we'll make sure the underlying logic is always crystal clear. So let's just start with that fundamental weirdness.
The wave-particle duality.
Yeah. To get to a point where a particle is passing through a solid wall, we have to let go of the idea that a particle is a solid little dot, right?
Right. If we assume everyone listening knows the basics of an electron and, basic kinetic energy, the real leap is this duality. Back in the 1920s, Louis de Broglie didn't just suggest particles act like waves, he suggested they actually are waves.
Waves of probability.
Exactly. That is the essential mental shift you have to make. When we talk about an electron today, we can't think of a tiny billiard ball hurtling through space. You have to picture this fluid, sort of undulating cloud.
Like a mist.
Yeah, a mist that represents the mathematical likelihood of finding that electron in any given location. It's governed by the wave function, which physicists usually denote with the Greek letter Ci sign.
Okay, so when the wave function is highly concentrated in one spot, you just have a high probability of finding the electron there if you measure it.
Right, if you check, it's probably going to be where the cloud is thickest.
So let's do a thought experiment. If I have an electron inside a microscopically small, completely solid box, the classical view is simple, right? The electron is inside. End of story.
It hits the wall, it bounces back like a rubber ball.
Right. But the quantum view brings in Werner Heisenberg and his uncertainty principle.
This is where it gets weird.
Extremely weird. So if I start shrinking that box, making the walls close in tighter and tighter, I am basically forcing the position of that electron to become extremely well-defined. I am pinning it down.
And the universe, at a fundamental level, absolutely refuses to allow you that kind of certainty. It won't let you know both position and momentum simultaneously.
Wait, so it's not just that our microscopes aren't good enough?
No, not at all. It is not a flaw in our measuring equipment. It is a hard-coded rule of reality. As you squeeze that box and you define the electron's position with greater and greater precision, its momentum, its energy of motion becomes violently uncertain.
It kind of freaks out.
Yeah, the wave function begins to fluctuate wildly. It starts pushing against the confines of the box.
Okay, if I am tracking that right, the box doesn't break physically, right? But the mathematical wave describing the electron just starts, bleeding into the wall itself?
It does. When the wave function hits the solid barrier of the box, it doesn't just stop or bounce cleanly. It penetrates.
Into the solid wall.
Yes. Now, inside the solid barrier, the wave decays exponentially. Imagine a sound wave hitting a thick concrete wall. It gets muffled really rapidly.
Sure.
But if the wall is thin enough, the wave doesn't fade to zero before it hits the other side. A tiny non-zero tail of that probability wave emerges on the exterior of the box.
Which means there is a non-zero chance that if I open the box, it's empty, and the electron is just sitting outside.
Exactly.
It didn't break the wall, it didn't go over the wall, it just tunneled.
That's quantum tunneling in a nutshell.
But let me push back on this with a macroscopic hypothetical, because this is what everyone always asks.
Oh, I know where this is going.
You do. If I am made of trillions of these quantum particles, right, and they all have probability waves, if I go lean against a solid brick wall for a very, very long time, is there a statistical probability that my entire body will just gently tunnel through to the other side?
It is a brilliant way to test the limits of the theory. The short answer is no.
Tragic.
I know, no walking through walls today. But the mechanism of why it fails is what's really fascinating. The probability of tunneling is violently sensitive to two things: the width of the barrier and the mass of the object.
Okay, so electrons are light.
An electron's mass is astonishingly small. You, on the other hand, are incomprehensibly massive on the quantum scale. Because of your mass, the wave function representing your entire macroscopic body decays so rapidly upon hitting the wall that the tail on the other side is practically non-existent.
It just drops to zero instantly.
Basically, yes. And furthermore, for a macroscopic object to tunnel, all your constituent particles would have to maintain quantum coherence.
Meaning they'd all have to act together.
Right, they'd have to act as a single, undisturbed wave.
Wow.
In a warm, messy environment like a human body, particles constantly interact, causing decoherence. The wave function collapses instantly.
So the magic is strictly quarantined to the absolute smallest fragments of reality, completely isolated from environmental noise.
You could lean against that wall for a trillion lifespans of the universe, and it still wouldn't happen.
Good to know. But that sensitivity to mass and barrier width, that's governed by a very specific equation, right? Our sources outline the transmission coefficient formula.
Yes, the math behind the magic.
It's usually simplified to T is approximately equal to E to the power of negative 2KL. And I want to unpack this slowly because it's kind of the master key to everything we'll discuss today.
Let's do it. Let's translate that math into a physical reality for you listening. T is the transmission coefficient. That is simply the probability that our particle successfully appears on the other side of the wall.
Okay, so T is the chance of teleporting, essentially.
Exactly. On the other side of the equation, we have E, which is Euler's number. It's the base of the natural logarithm.
Right, it's the universe's default rate for exponential growth or decay.
Spot on. But the real mechanics, the levers we can pull, live in the exponent, the negative 2KL.
Okay, let's look at those variables. L is the width of the barrier. So if the wall gets thicker, L goes up.
Correct. And K is a wave number that represents the relationship between the mass of the particle and the height of the energy barrier it's facing.
So if the particle is heavier, or if the energy required to classically climb the wall is higher, then K increases.
Yes. And because it's a negative exponent, any increase in L or K drives the overall probability down.
But it's an exponential drop, not a linear one.
That is the crucial insight here. There's an exponential decay. If you add just a single atom's width to the thickness of a barrier, you don't just reduce the chance of tunneling by a few percent.
Like it doesn't drop from 10% to 9%.
No. You might drop the probability by a factor of 10 or 100 or 1,000, depending on the material. The wave is suffocated almost instantly.
The sensitivity is just terrifying. A single atom changes the whole game. But here's the part of the source material that genuinely confused me at first.
Oh.
Yeah, so we have this formula, we know what goes in one side, and we can calculate the exact probability of what comes out the other, but for a century, physicists called the actual interior of the barrier a forbidden region. The texts talk about the mystery of the inside.
Ah, yes, the classically forbidden zone. For decades, the standard Copenhagen interpretation of quantum mechanics essentially said, don't ask what happens inside.
Just ignore it.
Pretty much.
Yeah.
The particle's on the left and then it is on the right. Asking what it was doing while tunneling was considered a completely meaningless question.
I'm meaningless.
Because observing it inside the barrier would require an energy transfer that would collapse the tunneling state entirely. It was treated as a black box. You literally couldn't look without destroying the phenomenon.
So we were basically watching a car enter a pitch-black tunnel through a mountain and then exit the other side.
Right.
We knew the entry and exit times, but we had absolutely no idea if the car changed lanes in the dark, hit the brakes, or, scraped the wall.
That is a highly accurate way to frame the frustration of physicists for a very long time. But recently, experimentalists have developed something called weak measurement.
Weak measurement, meaning what exactly?
Instead of hitting the tunneling electron with a high-energy photon that would instantly destroy the experiment, they use incredibly subtle probes.
Like a gentler way of looking.
Exactly, sometimes involving the spin of the electron acting like a tiny clock to gather partial information without fully collapsing the wave function.
And the sources mentioned they found evidence of an under-the-barrier recollision, which sounds violent. What exactly is colliding with what in a forbidden zone?
Well, it turns out the electron isn't just a ghost passively sliding through. While mathematically inside the barrier, the electron's wave function can actually interact with the potential energy field of the barrier itself.
Oh, wow.
It can essentially bounce or scatter off the internal structure of the forbidden zone. It proves that the inside is a real physical space where interactions occur, not just some mathematical transition between two states.
Which naturally brings up the Hartman effect, which is probably the most controversial thing in these physics texts.
Oh, definitely.
If we are tracking the particle inside the tunnel, how fast is it moving? The Hartman effect implies it might be breaking the speed of light.
This has kept physicists arguing for decades, literally. Thomas Hartman discovered in 1962, if you calculate the time it takes for a wave packet to tunnel through a barrier, the time becomes constant, regardless of how thick the barrier is, once the barrier reaches a certain width.
Wait, let me get this straight. If the time stays the same, but the barrier is getting thicker, then the effective speed of the particle has to be increasing.
You think so, yes.
And eventually, if the barrier is thick enough, it would have to cross that gap faster than light.
Exactly. And that threatens special relativity, which dictates that no information can travel faster than the speed of light, see?
So how do we reconcile that? Did we break physics?
Not quite. To reconcile this, we have to look at how we measure a wave. A wave packet is a group of waves clustered together. It has a leading edge, a peak, and a trailing edge.
Okay, picture a lump moving through space.
Right. The barrier acts like an incredibly aggressive filter. It preferentially dampens the trailing edge of the wave packet while letting the very front edge through.
So it's not that the entire particle sped up, it's that the front of the wave survived and the back of the wave was kind of shaved off.
Yes.
And that creates an optical illusion that the peak of the wave arrived faster than it should have.
That is the leading consensus right now. We're measuring the phase velocity, not the signal velocity. The information itself isn't traveling faster than light.
Okay, so Einstein can rest easy.
For now, yeah. Early models, like the Bohr-Heisenberg formulations, viewed this through the lens of the energy-time uncertainty principle.
Which means what, in plain English?
They conceptualized tunneling as a transient violation of energy conservation. For a vanishingly tiny slice of time, a particle could essentially borrow enough energy from the vacuum to climb over the wall.
Just borrow it from nowhere.
Yes, as long as it paid the energy back so quickly that the universe couldn't technically measure the debt.
I absolutely love that framing. It's like a cosmic accounting loophole.
It really is.
You overdraw your checking account to buy a house, but you deposit the funds a nanosecond before the bank's auditor runs the ledger. No rules were technically broken on paper.
It is a very soothing way to think of a chaotic process. And nature, in its infinite pragmatism, didn't just leave this as a mathematical curiosity on a blackboard. It weaponized this loophole to build the universe.
Which brings us back to the sun. This is where the abstract physics becomes the literal reason we are alive. Let's talk about nuclear fusion.
Inside the core of the sun, you have a plasma of unbound protons. And protons have a positive electrical charge.
Right.
And the electromagnetic force dictates that like charges repel. As two protons approach each other, they experience an electrostatic barrier called the Coulomb barrier.
Okay, so that's the invisible wall in this scenario.
Exactly. It acts like a steep, unscalable mountain of repulsive energy between them.
So to get them to fuse together, which is what creates heavier elements and releases the massive energy that eventually reaches Earth as sunlight, you have to smash them together with enough force to overcome that Coulomb mountain.
Yes. You need kinetic energy, which in a gas or plasma translates to heat. You heat them up, they move faster.
Makes sense.
But when astrophysicists calculated the temperature of the sun's core, around 15 million Kelvin, they realized the protons simply weren't moving fast enough.
It's too cold.
By the rules of classical thermodynamics, the collisions are too soft. The protons should just bounce off each other's repulsive fields forever.
So why doesn't the sun just sit there as a warm, dark cloud of gas in the middle of our solar system?
Because the protons are quantum objects. They have wave functions. When two protons collide at 15 million degrees, they don't have the energy to go over the Coulomb barrier.
But they get close.
They get just close enough that their probability waves overlap with the barrier itself. And thanks to our transmission formula T, is approximately equal to e to the negative 2kL, there is a vanishingly small but real probability that one proton will tunnel right through the repulsive field and manifest on the other side.
And once it's on the other side, the repulsive mountain is behind it. It's close enough for the strong nuclear force to just take over.
Exactly. The strong nuclear force operates only at incredibly short ranges, but it is vastly stronger than electromagnetism.
Huh?
Once the proton tunnels into that intimate range, the strong force snaps them together like supermagnets.
And that snap releases energy.
It releases a photon of energy. This is governed by something called the Gamow peak, which calculates the precise sweet spot where the protons have enough thermal energy to get close, thereby maximizing the tunneling probability.
That is just incredible to think about. Every ray of sunlight that hits your face is the result of a probability wave cheating its way through a magnetic mountain.
Every single one.
And you mentioned Gamow just now. The sources show that in 1928, George Gamow actually used tunneling to explain the exact opposite of fusion. Like, how heavy elements decay.
Right. Alpha radioactive decay. So elements like uranium or radium are unstable. They spontaneously eject an alpha particle, which is 2 protons and 2 neutrons bound together.
Okay.
Gamow looked at the nucleus of these heavy atoms. The strong nuclear force creates a deep energy well that holds everything together. The alpha particle is trapped at the bottom of this well, completely surrounded by a massive energy barrier.
And classically, it does not have the kinetic energy to climb out of the well. It should be trapped in there forever.
But Gamow realized the alpha particle is constantly moving inside the nucleus, constantly bouncing against the walls of the energy barrier. And every single time it hits the wall, its wave function probes the barrier.
It rolls the dice.
It rolls the dice, exactly.
So it's basically trapped in a casino where the odds are overwhelmingly against it, but it gets to play trillions of hands a second.
That is a phenomenal analogy. The probability of tunneling through the nuclear barrier might be 1 in a trillion, but the alpha particle is bouncing back and forth 10 to the 21st times per second.
That's a lot of zeros.
So eventually, against all classical odds, it hits the jackpot. The wave function extends far enough, the particle tunnels through the strong force barrier, and it goes flying out into space as radiation.
Wow.
Gamow used this exact mechanism to explain why some isotopes have a half-life of milliseconds and others have a half-life of billions of years. It strictly depends on the precise width of the barrier it has to tunnel through.
Because of that exponential drop-off we talked about earlier, LL, it's amazing how a shift of a fraction of a nanometer in barrier width can change a half-life from a fraction of a second to the age of the universe.
The math doesn't lie.
It doesn't. But nature uses this on a much more delicate scale, too. Let's move away from stars and radiation for a second. The texts dive into quantum biology, specifically cellular respiration, which just blew my mind.
Oh, this is a beautiful area of research. Yes, the machinery inside your own cells. Inside your mitochondria, energy is produced by passing electrons down a chain of protein complexes.
The electron transport chain.
Right. But the physical distances between the active sites on these proteins are sometimes way too far for classical physics to allow an electron to just hop across.
Like, the gaps are literal physical voids.
So they tunnel. The entire process of you metabolizing oxygen and generating ATP, the energy currency of your cells, relies on electrons tunneling across gaps of 15 to 20 angstroms between proteins.
So without quantum tunneling, I wouldn't have the energy to sit here and talk to you.
You wouldn't exist. And it's not just electrons. Protons, which are hydrogen nuclei, tunnel during enzyme catalysis.
Enzymes, like the things that speed up chemical reactions in our bodies.
Yes, they speed up reactions, and they often do this by positioning molecules so precisely that a proton can tunnel from one molecule to another, completely bypassing the massive activation energy required to move it classically.
The one that really stopped me in my tracks was the Loden DNA mutation theory mentioned in the sources. The idea that quantum tunneling could be the engine of evolution itself.
For Olaf Loden proposed this back in the 1960s. Your DNA is a double helix, right? Held together by hydrogen bonds between the base pairs adenine to thymine, cytosine to guanine.
The rungs of the ladder.
Exactly. And a hydrogen bond is essentially a proton shared between two molecules. Normally that proton sits in a stable energy valley on one side of the bond.
But because it's a quantum object, it has a probability wave. It's not just a stationary dot.
Exactly. The space between the two sides of the DNA base pair is a double well potential barrier. There is a small probability that the proton can tunnel across the barrier to the other side, creating what's called a tautomeric shift.
Okay, so the proton just blinks to the wrong side of the ladder.
Right. The proton is now in the wrong place. If the two strands of DNA happen to separate for replication, while that proton is tunneled to the wrong side, the replication machinery misreads the base pair.
It thinks it's a different letter?
Yes, so it inserts the wrong complementary base.
It hard codes a mutation. So a random error in the genetic code, the very thing that drives natural selection and the diversity of life on Earth, could be the result of a single wave function bleeding through an atomic wall at exactly the wrong millisecond.
It is a very humbling thought. Nature has been using this to mutate DNA in power stars for billions of years, but humanity only recently figured out how to domesticate it.
Which brings us to the device sitting in everyone's pocket right now. I want to transition from how nature uses it to how we exploit it and sometimes suffer from it in modern technology.
The silicon crisis.
Let's talk about the silicon crisis and Moore's law. Because if you are listening to this right now, you likely have a smartphone, a USB drive, or a solid-state drive nearby. They all use NAND flash memory.
They do. Have you ever thought about how a USB drive actually retains your photos and files for years without any power source?
I'll be honest, I always assumed it was magnets or something. You unplug the RAM in your computer, the data's gone in a second because the voltage drops, but the USB drive just remembers.
It's not magnets. The sources explain it's actually quantum tunneling, specifically something called Fowler-Nordheim tunneling.
Okay, break that down for us. How does that store my vacation photos?
Inside a flash memory chip, the basic storage unit is a specially designed transistor. It has something called a floating gate.
Floating gate, got it.
Think of it as an inescapable microscopic cage made of conductive polysilicon, completely surrounded by a thick, highly insulating layer of silicon dioxide.
So classically, if you put an electron inside that cage, it cannot leave. The silicon dioxide is a massive energy barrier. It's trapped.
Precisely. To write data, to store a 1 or a 0, we apply a relatively high voltage, maybe 15 to 20 volts, across the insulator.
Okay.
This massive electrical field physically warps the energy barrier of the silicon dioxide, turning it from a thick, insurmountable rectangular wall into a very thin triangular slope.
Ah. And we know from earlier that if you thin out the barrier, the L in our equation drops, and the transmission coefficient skyrockets.
Exactly. The electrons tunnel through the newly thinned barrier right into the floating gate. Then you remove the voltage. The barrier snaps back to being thick and rectangular.
And the door is slammed shut, the electrons are trapped.
At normal temperatures and without high voltage, the probability of them tunneling back out is so astronomically low that manufacturers can guarantee data retention for 10 to 20 years. We deliberately manipulate the shape of the barrier to force a quantum event.
We basically use the cheat code to teleport the electrons in, and then we close the door. It's brilliant. But as brilliant as that is, the texts make it incredibly clear that tunneling is also becoming our biggest nightmare in standard microprocessors.
Oh, it's a massive headache for the industry.
It is actively threatening Moore's law.
Moore's law is the observation that the number of transistors we can pack onto a microchip doubles roughly every 2 years. To keep that pace, the industry has spent decades shrinking the physical size of transistors.
Right, smaller transistors, faster computers.
But a standard MOSFET transistor works kind of like a drawbridge. You apply a voltage to the gate, the bridge lowers, and electrons flow across the channel. You remove the voltage, the bridge goes up, and the flow stops.
But the bridge is actually an insulating barrier, right?
The gate dielectric.
Yeah.
And as we have shrunk transistors down below the 10 nanometer node, heading toward 3 nanometers and below, that gate insulator has become shockingly thin.
How thin are we talking?
We're talking about walls that are only a handful of individual atoms thick.
And if we go back to our formula, T is approximately equal to E to the negative 2k L. If L, the thickness of the wall, is only 3 atoms wide,
The transmission probability is no longer near zero.
it becomes substantial.
Very substantial. The classical drawbridge is utterly useless at that scale. The switch is turned off, but the wave functions of the electrons in the source simply bleed right through the gate insulator or directly across the channel.
They just tunnel across the gap.
Yes, this is called quantum leakage.
So the transistor is essentially broken. The electrons flow when they aren't supposed to. They ignore the stop sign.
It causes massive static power dissipation. Even when your phone is asleep doing absolutely nothing, billions of transistors are leaking current because of quantum tunneling.
So that's why my battery drains when I'm not even using the phone.
Part of the reason, yes, it drains the battery and generates a tremendous amount of heat. We can no longer build a classical wall out of atoms if the wall is only a few atoms thick.
So how do we fix it? We can't just stop shrinking chips or computing stalls. We hit a wall. pun intended. The Patent Landscape Report highlights an alternative architecture called TFTs, or tunnel field effect transistors.
The TFT is a beautiful example of engineering jujitsu. Instead of trying to build thicker walls to stop the tunneling, the TFT completely abandons the classical drawbridge concept.
It leans into the problem.
Exactly. It uses the quantum leak as the actual mechanism to turn the transistor on.
So instead of trying to stop the leak, we use the leak to drive the engine. How does a TFET do that?
In a traditional transistor, you push electrons over a thermal barrier. In a TFT, you use different semiconductor materials to create a staggered band gap.
What does that look like?
You have a valence band full of electrons on one side and an empty conduction band on the other. But they are misaligned. They are totally different energy levels.
So they can't tunnel because there is nowhere for them to go at their current energy state. They're basically looking at a brick wall.
Exactly. The switch is firmly off. But when you apply a very tiny voltage to the gate, it bends the energy bands, it pulls the empty conduction band down until it exactly aligns with the full valence band.
The shelves align.
Yes. And because the barrier between them is so incredibly thin, the moment those energy levels align, massive band-to-band tunneling occurs. The current shoots across instantly.
And the data from that European research project on TFTs is just staggering because you aren't physically pushing electrons over a massive hill, but rather just gently shifting the energy levels to allow a quantum teleportation. The voltage required is minuscule.
It's tiny. They drop the required gate voltage from 1 volt down to 0.2 volts.
That lowers power consumption by 2 orders of magnitude.
100 times less power. It also breaks the physical limit of how sharply a transistor can turn on, known as the subthreshold swing.
Subthreshold swing, meaning how fast it goes from 0 to 1.
Yes. Classical transistors are hard-capped at 60 millivolts per decade of current increase at room temperature. TFTs can achieve much steeper swings, meaning they switch from off to on much faster and cleaner.
If we perfect TFT manufacturing, it could completely revolutionize mobile computing by drastically reducing power consumption.
It's a complete paradigm shift.
It really is.
Yeah.
But to truly understand how we manipulate these energy bands to control tunneling, I want to take a brief pause. We need to look back to a Nobel Prize-winning discovery from the 1950s. But first, a quick reminder. If you are enjoying this deep dive into the quantum realm, please take a moment to like and subscribe to this video brought to you by Decoding the Dark. We'll be right back. Welcome back. We were just discussing how modern processors are trying to adopt tunneling architectures to save Moore's law. But the concept of deliberately aligning energy bands to create a tunneling switch isn't new at all. The sources trace it back to Leo Esaki in 1957.
Yes, the invention of the tunnel diode, also called the Esaki diode, which earned him the Nobel Prize in 1973. Esaki was working with p-n junctions,
which are the building blocks of most electronics.
Right. A standard diode is made by joining a p-type semiconductor, which has a deficit of electrons, meaning it has what we call holes.
Empty spaces.
Exactly. You join that with an n-type semiconductor, which has an excess of electrons.
And where they meet, they form a depletion region, which acts as a barrier. Electrons normally need a significant voltage push to climb over that barrier to create a current.
But Esaki decided to heavily dope the materials. He injected a massive concentration of impurities into the silicon or germanium, about 1,000 times more than you would in a normal diode.
Why add so many impurities?
This extreme doping did something remarkable to the depletion region. It squeezed it down to a width of just a few nanometers.
So the LNR equation shrinks dramatically.
Yes. The barrier becomes so incredibly thin that electrons no longer need to climb over it. At 0 voltage, the system is in equilibrium. But if you apply just a tiny forward voltage, the energy levels of the excess electrons on the n side align perfectly with the empty holes on the p side.
The shelves align again, just like in the TFAT, and electrons tunnel straight through the barrier, current flows effortlessly.
But the magic of the Esaki diode is what happens next. It exhibits a bizarre property called negative differential resistance, or NDR.
This is the part that really bends the mind. Because in classical electronics, Ohm's law is king. If you increase the voltage, the pressure pushing the electrons, the current goes up. You push harder, more stuff flows.
But with NDR, as you continue to increase the voltage past a certain critical peak, the current suddenly plummets.
It drops.
It drops sharply.
It's entirely counterintuitive.
Yeah.
Instead of a car analogy, let's use a train analogy. Imagine 2 trains running side by side. One train is packed with people. Those are our electrons on the inside. The other train is completely empty. Those are the available holes on the p side.
I like where this is going.
So the trains are moving at different speeds. The space between the trains is our tunneling barrier. When the voltage is just right, the windows of the packed train exactly align with the windows of the empty train. For that split second, people can effortlessly step from one train to the other. That is our peak tunneling current.
Perfect analogy.
But if you keep increasing the voltage, it's like speeding up the packed train. Suddenly the windows don't line up anymore.
Right, they misalign.
The people are looking out at the solid metal wall of the other train. There is nowhere for them to go.
Exactly. By increasing the voltage, you have pushed the energy bands out of alignment. The electrons on the N side are now facing a forbidden band gap on the P side.
They just see a wall.
Because there are no available states at that specific energy level, the wave function has nowhere to exist on the other side. Tunneling stops instantaneously. The current drops precipitously, even though you are applying more electrical pressure.
And because this relies on quantum tunneling, which happens essentially instantly, rather than the slow physical drift of charge carriers over a barrier, this switching mechanism is incredibly fast.
It is blindingly fast. Resonant tunneling diodes, which are advanced versions of Esaki's concept, using incredibly precise quantum wells, can operate at terahertz frequencies. That's trillions of cycles per second. They are crucial for high-frequency microwave oscillators and specialized sensors today.
It's phenomenal. We learned how to crash the trains to make a switch. But this mastery of nanoscale gaps didn't just give us fast electronics, it gave us a way to visualize the invisible. We have to talk about the scanning tunneling microscope.
Oh, the STM. Invented by Gerd Binnig and Heinrich Rohrer in 1981, it won them the Nobel Prize in 1986.
They really handed out a lot of Nobels for tunneling.
Deservedly so. Before the STM, atoms were theoretical constructs we understood through scattering data. We knew they were there, but we couldn't see them. The STM allowed us to literally map the topography of reality atom by atom.
And it doesn't use lenses or light, it uses the mathematics of tunneling.
So, wait, how do you see an atom without light? I mean, classically, you need a photon to bounce off something to see it, right?
Right, you do. But with an STM, you don't actually see it. You feel it with probability.
Feel it, like physically touching it.
No, actually, you never let them physically touch. You use a conductive metal tip, usually made of tungsten or platinum iridium.
Okay.
And this tip is sharpened so incredibly precisely that the very point of it terminates in a single solitary atom.
A needle that is literally one atom wide at the tip.
Exactly. You bring this tip incredibly close to the surface of a conductive sample, say a sheet of gold, but you leave a gap of empty space, usually a fraction of a nanometer.
Just a tiny vacuum gap.
Right. And classically, empty space is a perfect insulator. No current can flow through a vacuum.
But quantum mechanically, if you apply a small voltage between the tip and the sample, the electrons will tunnel across that vacuum gap. Yes, and here is where the exponential nature of our equation, T is approximately equal to e to the negative 2kL, becomes the ultimate measuring tool.
Because the current is tied to L.
Because the decay is exponential. The tunneling current is violently sensitive to the width of the gap. If you move the tip just 1 angstrom closer to the surface.
Which is, what, a 10 billionth of a meter?
Roughly the radius of a single atom. If you move at that tiny distance, the tunneling current increases by a factor of roughly 10.
That sensitivity is the key. So the microscope sweeps this single atom tip back and forth across the sample in a grid, a raster pattern.
As the tip sweeps horizontally, it encounters the bumpy terrain of individual atoms on the surface. When the tip moves over an atom, the physical gap shrinks by a fraction of an angstrom, and the current spikes massively.
And when it moves into the valley between atoms,
the gap widens and the current plummets.
But wait, if it's moving over bumps, why doesn't the tip just crash into the atoms and break?
Because of a brilliant feedback loop. A computer monitors the tunneling current constantly. If the current goes up, the computer knows the tip is getting too close, so it applies a voltage to a piezoelectric crystal holding the tip.
Piezoelectrics. Those physically change shape when a voltage is applied, right?
Yes, allowing for physical movement on the scale of picometers. The computer pulls the tip back just enough to keep the tunneling current perfectly constant.
So the computer is constantly lifting and lowering the tip to sort of surf the probability wave of the surface. And by recording exactly how much voltage it took to move the tip up and down, it creates a three-dimensional topographical map of the atoms.
It is an exquisite piece of engineering. But the challenges are just monolithic. Think about it. The gap you are maintaining is around 0.1 nanometers.
That's nothing.
If we think about environmental noise, the ambient vibrations of a quiet room, just people walking in the building next door or a truck driving a mile away, can cause the floor to vibrate by a micron.
Which is huge on this scale.
That is 10,000 times larger than the gap you are trying to hold.
So if the floor shakes a micron, that single atom tip slams into the gold surface and is just obliterated.
Exactly. So the vibration isolation has to be extreme. Early STMs used magnetic levitation. Modern ones use nested stages of heavy metal suspended by soft springs.
Springs?
Sophisticated ones. They employ eddy current damping, where copper plates pass between strong magnets. If the table vibrates, the movement of the copper through the magnetic field induces an electrical current that creates an opposing magnetic field.
Acting like a frictionless brake to deaden the vibration instantly.
Right, they're essentially isolating the experiment from the physical motion of the macroscopic universe, just to create a quiet enough space for an electron to tunnel.
And because they did that, we didn't just map atoms, we eventually learned to move them, which opens the door to the most complex machines humanity has ever conceived.
Let's move into section 7 of our outline, the quantum computing era. We're transitioning from macroscopic observations of single atoms to engineering microscopic systems that actually behave quantum mechanically.
The outline highlights the recent Nobel Prize in Physics for macroscopic quantum tunneling. This research completely validates superconducting quantum circuits. We are talking about machines built by companies like IBM and Google, which use qubits instead of classical bits.
Classical bits are deterministic. They're either a 1 or a 0. A qubit can exist in a superposition of both 1 and 0 simultaneously.
Right, which allows for parallel calculation on a massive scale.
To build a solid-state qubit that we can actually control, the industry heavily relies on superconducting circuits cooled to roughly 15 millikelvin.
Which is colder than deep space.
Much colder. And the heart of these qubits is a component called a Josephson junction.
Okay, let me make sure I'm getting this right. To build a Josephson junction, we are basically taking a loop of superconducting metal and purposefully breaking it with an incredibly thin layer of insulating aluminum oxide. We are building a deliberate roadblock.
That is exactly what it is. A deliberate atomic scale roadblock. In a superconductor, at those extreme temperatures, electrons overcome their mutual repulsion and pair up into what are called Cooper pairs.
So they sort of hold hands.
Basically. These pairs act as a single macroscopic quantum state. They flow without any electrical resistance whatsoever. When this macroscopic wave function encounters the insulating roadblock of the Josephson junction, it doesn't stop.
It tunnels.
The entire macroscopic state tunnels right through the barrier.
And it does this without any voltage applied. It's driven purely by the phase difference of the quantum wave on either side of the barrier.
Yes. The tunneling of these Cooper pairs is what introduces the necessary nonlinearity into the circuit, allowing us to isolate two specific energy levels to serve as our quantum 0 and 1. Without the tunneling across the Josephson junction, the superconducting qubit simply would not exist.
But the sources make a massive point here. Tunneling is the magic that makes the qubit work, but it is also the mechanism that actively destroys the computer's calculations.
It is the ultimate double-edged sword. Tunneling is fundamentally probabilistic. You want the Cooper pairs to tunnel only in response to very specific microwave pulses that represent your quantum logic gates.
You want to control the magic.
But the universe is messy. Sometimes energy from stray photons or cosmic rays, or just tiny thermal fluctuations, gives an electron enough energy to break its Cooper pair.
And then what?
It just spontaneously tunnels across the barrier, or even tunnels through the vacuum to a completely different qubit nearby.
This is what the texts refer to as leakage and crosstalk.
Right. Leakage is when your qubit absorbs unwanted energy and tunnels out of the computational 0-1 space into a useless higher energy state. Crosstalk is when the wave function of an electron in qubit A extends far enough that it tunnels into qubit B, completely scrambling the fragile entanglement you've carefully built.
It sounds infuriating for an engineer. You need strong coupling between the qubits to perform fast calculations, but making the physical connections closer increases the environmental noise, which inevitably triggers unwanted tunneling.
It is an agonizing balancing act. And if the calculation fails, you can't just pause the program to check the memory like a classical computer.
Right, because observing a quantum state collapses the wave function. The data is destroyed.
Exactly.
But the sources highlight an incredible workaround. They mention using machine learning and AI to mitigate these tunneling errors. But wait, How can a classical AI observe a quantum state to correct an error without collapsing it? That seems like a massive paradox.
It is a brilliant bit of physics called quantum error correction, and AI is supercharging it. You don't actually measure the data qubit itself. You entangle it with helper qubits called ancilla qubits.
Ancilla qubits, okay.
When unwanted tunneling occurs, say a phase flip error, it affects the entire entangled system. The AI measures only the ancilla qubit. Measuring the ancilla gives the AI what is called a syndrome, a clue about the parity of the system, without ever collapsing the actual data qubit.
It's like checking the shadow of an object to see if it moved without ever looking directly at the object itself.
Exactly. And because the error rates are so complex and non-deterministic, classical algorithms struggle to calculate the corrections fast enough. Researchers are training neural networks on massive data sets of quantum noise.
So the AI learns what the noise looks like.
The AI learns the subtle, invisible patterns of environmental noise that lead to unwanted tunneling events. It can read the syndrome from the ancilla qubit and instantly fire a precisely tailored microwave pulse back into the system to unflip the phase and correct the error in real time.
The sources say this improves error suppression by up to 30%. That is a massive leap toward fault-tolerant quantum computing. But there is another approach entirely mentioned in the texts, D-Wave systems. They don't build gate model computers like Google or IBM. They use something called quantum annealing.
D-Wave takes a completely different philosophical approach. Instead of trying to aggressively suppress unwanted tunneling with AI, they lean into it entirely.
They embrace the leak.
They do. Their processors are designed to solve massive optimization problems. Think of finding the most efficient route for a delivery fleet with 1 million variables, or finding the absolute lowest energy state of a complex folded protein for drug discovery.
Okay, to explain this, let's go back to an analogy. Imagine a massive, complex mountain range with thousands of peaks and deep valleys. The absolute lowest valley is the perfect, optimal solution to our problem.
A classical computer trying to solve this is like a blindfolded hiker. It starts at a random point, feels the slope of the ground, and walks downhill. Eventually, it hits the bottom of a valley.
But it has no idea if it's the lowest valley in the entire mountain range. It just found a valley.
Exactly. To find out if there's a better one, it has to expend massive computational energy to climb back up a mountain and search another valley. It is incredibly inefficient.
But a quantum computer using quantum annealing doesn't climb the mountains. It physically tunnels through them.
Yes. D-Wave's processors, which now have over 5,000 qubits, map the variables of your problem onto the physical layout of the superconducting loops. The system is initialized in a quantum superposition, essentially occupying all the valleys simultaneously.
It uses a transverse magnetic field, right?
Yes, they apply a transverse field, which creates a very high probability for the qubits to tunnel between different states. They are tunneling right through the energy barriers, separating those mathematical valleys.
And then what?
As the calculation proceeds, they slowly turn off the transverse field, raising the barriers back up. The system naturally physically relaxes into its absolute lowest energy state.
Wow.
It finds the deepest valley not by exhaustive searching, but by allowing the probability waves to literally leak through the energetic mountains until they settle at the global minimum.
That is profound. We are forcing the universe to do our math homework by letting it leak through reality. It is a stunning manipulation of nature. Which naturally brings us to our final frontier. We are pouring billions of dollars into overcoming these engineering hurdles. What exactly are we going to do with all this quantum power?
Section 8, Future Use Cases and Emerging Technologies. We are transitioning from the theoretical physics to the deeply practical applications. If we want to fully master tunneling, we need better materials to build our walls and pathways.
Right. The Patent Landscape Report focuses heavily on 2D materials. Graphene is the famous one, but they also highlight transition metal dichalcogenides, or TMDs, and hexagonal boron nitride, HBN. Why are these materials the future of tunneling?
It comes down to structural perfection. Hexagonal boron nitride, for instance, consists of alternating boron and nitrogen atoms arranged in a flat hexagonal lattice.
Yeah.
It is exactly 1 atom thick.
Okay.
In classical silicon manufacturing, when you try to make an oxide barrier extremely thin, the surface gets rough at the atomic level. It has ridges and valleys.
And because tunneling is exponentially sensitive to the width L, a bumpy barrier means the tunneling current is chaotic and unpredictable.
Precisely. But HBN is atomically flat. It provides a perfect, smooth, uniform barrier. When researchers stack these 2D materials like atomic Lego blocks, creating what are called van der Waals heterostructures, they can engineer tunneling pathways with absolute precision.
They literally build custom paths for electrons.
Yes, and the electron mobility in these structures can be up to 100 times greater than in silicon.
And because there is no classical resistance or thermal scattering slowing the electrons down, the reports indicate this allows for sub-picosecond switching speeds.
A picosecond is 1/1,000,000th of a second. This paves the way for processors that natively operate at terahertz frequencies without the catastrophic heat generation of current silicon.
And the money is rapidly following the science. Look at the pharmaceutical sector. The reports note that 42% of major pharma companies are investing heavily in quantum tunneling simulations.
The current paradigm for drug discovery is heavily reliant on trial and error. To accurately simulate how a new drug molecule will bind to a target protein in the human body, you have to calculate the overlapping wave functions and tunneling probabilities of thousands of interacting electrons.
Which a normal computer can't do.
A classical supercomputer simply cannot do it. It has to use approximations, which often leads to failed drugs in clinical trials.
But a quantum computer fundamentally operates using those exact same tunneling mechanics. It doesn't approximate the quantum interactions, it naturally simulates them.
Exactly. Using quantum annealing to find the lowest energy state of a molecule, the deepest valley, can show researchers exactly how a protein will fold or how a drug will bind.
So it takes the guesswork out.
Industry experts predict this could cut drug discovery cycles by 30 to 40%. We are talking about shaving years off the development of life-saving therapeutics.
We see a similar urgency in finance and security, too. Financial institutions are pouring massive capital into quantum-enhanced algorithms. If D-Wave can find the lowest valley in a molecular energy landscape, it can just as easily find the absolute lowest risk profile in a massive, mathematically complex portfolio of assets, executing the calculation in milliseconds.
And the energy sector is equally invested. Companies like BP and Shell are exploring quantum applications for grid optimization.
Why grids?
If you are managing a national smart grid integrating wind, solar, and battery storage across millions of nodes, the routing optimization problem is overwhelmingly complex for classical systems. Tunneling-based optimization can solve it. Furthermore, they're using these systems to model the atomic structures needed for highly efficient carbon capture materials.
It's poetic, really. We are using macroscopic quantum tunneling computers to simulate microscopic quantum tunneling to design better materials to fix the macroscopic climate.
It's all connected.
But bringing it all the way back to the listener, when does this escape the laboratory and hit our homes? What about consumer electronics?
The transition will likely happen in stages. Industry analysts project that within the next 5 to 7 years, we will see the introduction of hybrid processors.
Hybrid in what way?
These chips will use traditional silicon for basic logic tasks, but integrate tunneling-based components like TFTs or 2D heterostructures for specific high-speed calculation pathways.
Imagine a world where the processor in your smartphone is utilizing TFT architecture. It isn't fighting leakage, it's using the tunneling to sip power at 0.2 volts. Your battery life wouldn't be measured in hours, but in weeks, and the processor would be running exponentially faster than anything we have today.
That is the ultimate goal. When material science eventually perfects topological insulators, materials that maintain these delicate quantum states stably even at room temperature without the need for freezing dilution refrigerators, the entire landscape of human engineering will change.
Everything shifts.
We will transition from building classical machines that desperately try to ignore or suppress the quantum world to building quantum machines that just happen to exist in the macroscopic world.
It is a breathtaking vision. We have covered an immense amount of ground today. Let's gently recap this journey we've taken for you. We started with a purely theoretical math equation in the 1920s, a bizarre realization by de Broglie and Heisenberg that probability waves can leak through solid, impenetrable boxes.
We saw how that exact, terrifying mathematical sensitivity powers the nuclear engine of the sun, and how it drives both radioactive decay and the random genetic mutations that literally fuel biological evolution.
We watched it become the leaky, chaotic limit of our modern microchips, forcing us to invent incredible workarounds like the tunnel diode and the TFET. We learned how it gave us the ability to physically feel the topography of individual atoms using the STM by isolating a needle from the vibrations of the entire universe.
And finally, we look deep into the freezing, fragile heart of tomorrow's quantum computers, where we are actively harnessing teleporting electrons to solve the world's most impossible optimization problems.
It is a profound reminder that the universe simply does not respect our classical intuitions about boundaries. And as we close, I would like to leave you with one final conceptual thought to ponder.
Yes, please do.
If quantum tunneling proves that the foundation of the universe ultimately operates on fluid probabilities rather than rigid walls, what happens when humanity perfects the ability to manipulate those probabilities on a macroscopic scale? If we can flawlessly engineer the physical variables in that transmission equation, will the very concept of a barrier simply cease to exist in human engineering? Are we moving toward a future where we don't just break walls but render them mathematically irrelevant?
A world where the obstacle itself is just a probability waiting to be rewritten. That is a profound thought to sit with.
Thank you for taking this deep dive with us and letting us share this incredible microscopic landscape with you. Don't forget to like and subscribe to this video brought to you by Decoding the Dark. Until next time, stay curious, take a deep breath, and keep exploring.